So, hello friends, welcome back. So, in this lecture I will just go over all the topics or just the name of the topics that we have covered in this 12 week long course. And this course was on combustion in air breathing aero engines. Okay. And of course, combustion in air breathing aero engines is a complicated phenomena by now. Okay. But it has got several aspects to it. It has got the design aspects where you have to think about designing a combustor that can power a gas turbine engine, or it can power a scramjet or a ramjet engine. But those design aspects are intricately coupled to the fundamental processes that happens in the combustor. Okay. So, to design a combustor which is working, which is successful, which is efficient, one needs to know the fundamental combustion processes very well. So, that is why we have gone into this whole course essentially could be split up into 3 parts. The first part we have discussed fundamental combustion processes. Okay. So, if you remember, so here we have the modules, we have the topics in this. The first column is the serial number of the lectures, second column is the module it covered, third column is the topic it covered, and fourth column is the concepts that we covered. Okay. So, in this module chemical thermodynamics and kinetics, which was about 5 lectures, we first of course gave the introduction about the importance of combustion in air breathing aero engines, and how it is coupled to the high energy density of the liquid hydrocarbons. Then in chemical equilibrium we went into the topics of classical thermodynamics, maximization of entropy principle, Gibbs free energy. We talked about chemical equilibrium, the equilibrium constants, Kp, Kc if you remember. Okay. And then we looked into different things like heat of formation, and we discussed what is sensible heat, what is heat of reaction and combustion. We also discussed the concepts of sensible enthalpy and enthalpy of formation. Okay. So, those things are very important, whereas the total enthalpy is the sum of the sensible enthalpy and the enthalpy of formation. We discussed heat of reaction and combustion, and we said how we can estimate heat of reaction from the equilibrium constant, and then how we defined how we could estimate adiabatic flame temperature for a closed vessel which does not interact with the surroundings through energy transfer. Okay. And we showed that how adiabatic flame temperature concept essentially emerges from the concept of the conservation of energy. Okay. So, then we looked into chemical kinetics. Okay. We looked into law of mass action, which is the founding pillar of chemical kinetics. We looked into reverse reactions, we need to look into net reactions, and we looked into this multiple reactions, how to handle multiple reactions, the quasi steady state and the partial equilibrium approximations. We looked into reaction order molecularity, we looked into Arrhenius law, activation energy, and collision theory. Okay. Then we looked into this the concepts of activation energy, which comes in the Arrhenius law, where we said that your which was like your k is equal to e to the power b times t to the power of alpha times e to the power of minus activation energy by RT. Okay. And then the whole reaction rate becomes essentially this k, the reaction rate constant, times the product of the concentration of the reactants raised to their stoichiometric exponents. So, all these we discussed. We discussed how we can estimate this reaction rate constant by a rudimentary idea called collision theory, which does not take into account the energy states of the electron cloud surrounding the molecules. And as a result, we looked into this more advanced transition state theory, whereby invoking these 2-step reactions formation of an activated complex, we could form a better description of the reaction rate constant. We looked into unimolecular reactions, straight chain reaction, hydrogen halogen systems, branch chain reactions. This was very important, where we showed that under what conditions a system can lead to very rapid combustion, that is when these branching reactions can dominate and it can produce more and more chain carriers, and what are the criteria for that. And we also looked into the Flammarion inhibitors and experimental techniques to measure the different reaction rate constants. Then we looked into oxidation mechanisms of fuels. Practical fuels, we defined what is ignition delay. We looked into branch chain reactions, the hydrogen oxygen systems, Z curve. We looked into the competition between termination and the branching reactions, which defined one of the limits. We looked into oxidation of carbon monoxide and the role of initiation reaction. We looked into methane oxidation, ignition of light hydrocarbons and the phenomena that it entails, like cool flames and negative temperature coefficients, how the bond breaks in different hydrocarbons, beta scission rule, formation of NOx, Zeldovich mechanism, prompt NOx, etc. Those things that we discussed, the concepts of soot and PA formation in a very little bit tangential manner, in a very quick manner we discussed. Also we discussed very few aspects of the mechanism reduction. So then with this we were equipped with chemical thermodynamics and kinetics, okay, in this part. Next we looked into transport phenomena and governing equations. We looked into different forms of transport, momentum transport, heat transfer, as well as species transfer and the associated diffusion coefficients and derivations, okay, and how you can use the kinetic theory to discuss. Then we looked into the governing equations. We showed that all fundamental like conservation laws which are used to describe systems are essentially written for systems. So then for systems, how we can translate those laws for closed systems to open systems, like the flowing systems which are of interest for engine type of configurations. And that was done by the Reynolds transport theorem. So that led to this control volume formation and the Reynolds transport theorem. Then we looked into different constitutive relations, that is, after you derive the governing equations for control volumes, your job does not end, because there are several other equations and relations that needs to be supplied to basically to close the system of equations. We looked into diffusion velocities and auxiliary relations and isobaric assumption, and we looked into simplified diffusion control systems and energy equations. And then we derived the energy equation in an enthalpy form. We derived the species transport equations, and we incorporated the different ways by which we could simplify these reaction systems, simplify these governing equations by invoking the distinct diffusivity and distinct specificity and diffusivity formulations, okay. And this led to simplified equations, and but then after this we arrived at the simplified equations, we realized that this nonlinear reaction rate term creates a very big problem. So we tried to derive conserved scalar equations formulation by which we could derive a system of equations which describes the conserved scalar, where there is no such right hand side source or sink term. But of course we realized that this could not be avoided. So in one equation you have to solve for the reaction rate, because in a combustion system, of course, that is the what is the most important, okay. And then we looked into the derivation of coupling functions, local coupling function formulation. Then we moved into non-premix flame. We looked into the structure of a 1D chambered flame, which is which can be considered as an unit or the most fundamental of non-premix flames, by using concepts of coupling functions. So we reviewed the chambered flame and the coupling functions and invoked the reaction sheet approximation and its properties. Then we looked into condensed fuel vaporization, because as we know that all these engines use liquid fuels. So it is important to understand how these liquid fuels can evaporate and then mix and then react, because in air breathing aero engines the reactions invariably happens in gas phase. So it is imperative to know what is the mechanics and what is the heat transfer thermodynamics behind this liquid fuel evaporation and burning. So we looked into the d square law of droplet vaporization also, okay. Then we moved into laminar premix flames, where we looked into the thermodynamics of laminar premix flames, this Rankine-Hugoniot relation. We find out the difference between deflagration and detonation, and how does the properties before and after change for these kinds of different waves, deflagration and detonation waves. Then we looked into the structure of standard 1D flames, okay. We invoked the scaling analysis, and we found out the burning flux and as a function of pressure, and we found out that how burning flux is one of the most important properties of that defines the laminar premix flame, and what does it depend on. Then we looked into analysis and governing equations. We looked into the cold boundary difficulty, which happens when you want to solve for a 1D premix flame in a doubly infinite domain. Then to define to arrive at this things at this burning flux, analytically we invoked we took up this Zeldovich-Frank-Kamenetsky analysis, and then we looked into the laminar flame speed, the different types of flame speed dependence, how we can extract global parameters from overall complex set of reactions. We looked into the chemical structure of hydrogen in a flame, chain structure, thermal structure, and then we looked into the limit phenomena, ignition, extinction, quenching distance, adiabatic thermal ignition, non-adiabatic explosion, and then well-stirred reactor and S curve. Okay. By explosion, once again here we mean rapid combustion, where the rapid release of energy causes a quick increase in temperature. Okay. And then we looked into the well-stirred reactor and the S curve and the different like ignition extinction points at different Darm-Coulomb numbers. Then we looked into the limit phenomena, we looked into premix flame extinction, how does it extinguish, and the flammability limits. Okay. So with this, our concepts of this fundamental combustion process was done, and then we were in a position to understand turbulent combustion, because you see in an engine is a very complex turbulent flame. Okay. So but the individual unit part of a turbulent flame is essentially this fundamental combustion process that we have described. But so once we know the fundamental combustion processes, we can use those concepts to describe something bigger, something statistically to describe turbulent combustion. So then we looked into turbulent combustion, where we first started with non-reacting and reacting turbulent flows. We looked into turbulence first, where we spent a lot of time in analyzing the non-reacting turbulence concepts. We looked into how we can derive Rand's equations, how does the concepts of turbulent kinetic energy transport equation arrive, what are the how does production of turbulent kinetic energy happen, how does dissipation happen, and then once this turbulent kinetic energy is produced, how does this pass across different scales and gets dissipated into the Kolmogorov length scales. Okay, so we looked into the effect of we looked into this turbulent kinetic energy and cascade. We looked into Kolmogorov hypothesis, and we looked into the energy spectrum. We looked into the turbulence effect of turbulence on combustion, and we introduced the concept of Favre averaging or density weighted averaging. And then we looked into this eddy viscosity K epsilon model and the energy equation and reactive scalar formulations. Then we looked into the moment methods, where we wanted to average arrive at averaged description of this average governing equations or governing equations that describe average variables. But immediately we landed up in a closure problem, and we found that the nonlinearity of the reaction rate problem, nonlinearity of the reaction rate poses a major difficulty in its averaging. Okay. So then we looked into the dissipation and scalar transport. We looked into the gradient transport and the reactive scalar transport and scalar dissipation rate. We looked into rudimentary models to provide closures, where we discussed like eddy breakup and eddy dissipation models, Spalding's theory of EBU eddy breakup concepts. We looked into then turbulent non-premixed combustion, where we showed different types of non-premixed turbulent flames, and then we introduced the concept of mixture fraction. And once the mixture fraction concept of was introduced as a conserved scalar, we also discussed the average, the transport equation for Z, and to close them, how one can use this presumed shape PDF approach and the Favre averaged equation. Then we because this mixture fraction emerges as such an important quantity, we said that one could even transfer, or one could even write the governing equations with mixture fraction as the independent variable. So that led to this Krokot transformation in the Z space. So we transformed all these energy equations into mixture fraction space, and that led to the emergence of the scalar dissipation rate as a characteristic diffusivity. And then we discussed the different timescales in non-premise combustion. We touched upon conditional moment closure modeling, and we touched upon also the regimes of non-premise combustion. So, with that we went into turbulent premix flames, where we discussed at length the concepts of regime diagrams, the interpretation of the Darm-Colon number, Kolovitz number, the other flame speeds and the flame stretch concepts. We showed the G equation and the models for flame speed in G equation, and then we looked into the turbulent burning velocity and the turbulent flame speed derivation. We showed the experiments of turbulent flame propagation rate, contemporary experiments, and we finished it off with the Bray, Moss and Libby model. Okay. Now, this was the final part. So, we now have understanding of the fundamental processes of combustion. We know how we can describe turbulent combustion using this part. So, now we can go into the different applied aspects of our aero engine combustors and the associated processes. Okay. So, the whole thing is that the combustion happens in all these engines at intensely turbulent flows. So, it is important to understand the fundamentals to even appreciate what happens in a gas turbine engine and to develop capabilities on how to model them. So, of course, one of the most important engines around is the gas turbine engine, and we looked into the aero gas turbine combustors. So, where we looked into we introduced the basic design features and how how the modern gas turbine combustor essentially evolves from a straight duct, why it needs a diffuser, why it needs flame swallowers, all these things, and then we looked into the different zones in a combustor. We looked into the different types of combustors, can annular combustor, and we looked into the flames in swirling flows. And then we looked into the different zones of the combustors, the primary zone, the dilution zone, the primary zone and the dilution zone mainly, and how those can be used coupled to achieve desired pattern factor, which is very important for the life of the turbine. Okay. But of course, this aero gas turbine engines works with liquid fuels. So, it is important to understand how liquid jet breaks up, because so far we have understood how the droplet evaporates. So, but taking a step back, now we needed to understand how the liquid jet essentially breaks up, so that the surface area can be increased by forming small droplets, and now the small droplets can evaporate and mix and burn. So, for that liquid jet breakup, we looked into Rayleigh-Plateau instability, the fundamentals, and then we looked into different atomizers and cooling techniques. Okay. So, in the following, then we looked into flame stabilizations, and for that we introduced afterburners, and we introduced bluff body flows and the different blow off correlation. We discussed at length the principles and the applications of laser induced fluorescence. That is, we need to understand how the species field evolves inside a real combustor. So, for that one of the ideal techniques is to use laser induced fluorescence, and it is a planar counterpart on the planar laser induced fluorescence. Also, we looked into particle image velocimetry. We looked into the different blow off stages. The particle image velocimetry was used to understand the flow fields of this combustion inside the combustor, in the flow field in a flame which is stabilized by a bluff body. Then we looked into the different blow off stages. We looked into the blow off mechanisms, and that emerges from the small scale laboratory experiments. And then we discussed the blow off mechanism using laser diagnostics from a prototypical afterburner. That was these experiments are done at University of Connecticut. And finally, we looked into this scramjet combustion in scramjet, where we introduced the scramjet. We introduced steady 1D analysis of frictionless flow with heat addition in constant cross section. We looked into different processes in scramjets like mixing, and then we looked into ignition, burning timescales, and flame stabilization. So, that is all we have covered for this course. It is a lot of material that we have covered, and I hope that you will find this useful and find it exciting to pursue one of these or many of these topics further in your career. So, I will finish off with these acknowledgements. First of all, thanks to my PhD advisor, Professor B.M. Setijan. I have presented many of the works that we did together at University of Connecticut. To my postdoc advisor, Professor C.K. Law at Princeton University, and many of the notes he generously gave, and which I have taken some parts of that and have been modified them and used this in this course, of course with his permission. And then my colleagues at the Department of Aerospace Engineering and the Institute for their support. To my students, acknowledgements are due to my students Ankit, Abhijit, Arnab, Nimesh, Raju and Lakshmi for their inputs. And of course, my PhD students Harsh and Himanshu has been instrumental in realizing in this course in making many of the slides, editing them, modifying them, as well as preparing them, as well as with the assignments and the question papers. Their help is acknowledged. And to many papers and the books that have been used, we have used numerous materials from numerous papers and books with citations, of course. If there are any omission, apologies for that. And to the great, wonderful and NPTEL staff, Ms. Vidya, Ms. Guru Raja, Mr. Guru Prakash and Mr. Avinash, who have patiently worked with me throughout this course. To IIT Madras for coordinating this great initiative, to ISC for coordinating this great initiative, and of course acknowledgements are due to you, to the students, only whose learning can make this course a success. And finally, acknowledgements to my family for their patience. So thank you very much. Hope you enjoyed this course.